Away we go. All right, so gas review. We have roughly 9 questions, some A's and B's. Most of them are calculations. Some of them, a few are short response, though. I have set it up in such a way that hopefully you can fit most of it to the right side, if you'd like. I think that would be a positive for you. So I want to do this first one, get you started with it, actually. I want to do the second one with you fully, okay? So let's take a look at this. It says HCl, and it says gas. Reminder, this is a gas test. And I'm saying that now to help you with the next problem, but you can only put gases in a gas law. When we're dealing with gases, you've got to recognize when it's a gas or when it's not. If it's a solution, that might not apply to what we're dealing with. Can be prepared by a reaction of NaCl with sulfuric acid. What mass of NaCl is required to prepare enough HCl to fill a 340 ml container or cylinder to a pressure of 151 atm at 20 degrees Celsius? So this, if you haven't realized yet, is a gas stoichiometry problem. Okay, I see it because I have some compounds. I'm talking about other compounds, so I need the equation. Okay, I need an equation. I need a chemical reaction. So it says HCl can be prepared. So that would be a reactant or product. Prepared. It's going to be prepared. So it's product. How do I know that? By reaction of NaCl with H2SO4. It sounds like those two things are reacting. So those are my reactants. What's my other product? Na2, good. That's good. Na2SO4. Because you got to bring that 2 down, right? So then we got to just make sure we balance this. There I am. There will not be an equation that you aren't prepared for, meaning it's going to be like a double or a single. Like you should be able to recognize what's happening. If you make a small mistake with a coefficient or a number, everything's still on the table for you to be successful on. It might mess up a mole ratio or something like that, but again, we'll figure out the mistakes you made through it. So it says what mass? Organize your information. I want to know mass of that, and it's saying what mass of NaCl is required to prepare HCl to fill this. So I have some volume, and you can write it if you want. Today I'm going to. On a test, you might not write that. You might just write V, like I got V here, and I got the P, and I got my T. And it's not a bad idea maybe on a test to not actually write all the numbers. Just say, I have a V, a P, and a T. So, am I starting with a gas law and ending as its T-chart, or am I starting with a T-chart and ending on a gas law? Think about it for a second. I mean, so that's my flow chart. That should always be in our heads. So I'm looking for grams, right? So I have to end here. So right there, that's already a sign of what the heck is happening. I have of these 3 things. This is a volume, this is a pressure, this is a temperature. The only one that exists on this flow chart is volume, correct? It's the only one. So I have to be able to get onto my flow chart. So I need, and I just said I wasn't going to do any of this. All right, I'm going to be quiet. So I'm going to pause this if you're watching this at home, finish this up. You guys start it up. So if you plug this in, I would love when you're doing any kind of ideal gas law and you're finding 2 different compounds that you would do a little subscript. I'm not going to mark off, but I think it's a real good way of approaching things. I'm solving 4 moles of HCl, and it gets you it's clear what you're solving for. So I have my moles. This is what we got. Hope. Anybody else? 21? Did I just miss? Did I miss it? Oh, I see what I did. Is it just off by a factor of 10? I think I missed the 0. I got that. If you're off by a little, it might be based on numbers that you're using, unless it's exactly the same. Anybody else get this? No? So now I just have to recognize where you are. If you know where you are and you understand this flow chart, you should be good. So now we're doing mole ratio for every 2 moles of HCl. In this case, I happen to have 2 moles of NaCl. Obviously, we're all going to round a little differently. And I get 124.5. I don't have answers in these. Everyone's nodding their heads, and I feel good about it. All right, so we had to start with an ideal gas law, and then we use the T-chart to kind of get us home. So you just got to recognize where you're at. Whenever you're getting in the problem, I might give you the equation, but if you don't get the equation, make sure that you are setting it up. And worst case scenario, your mole ratio is off. You might be off by that, but that, to me, I'd recognize what you did wrong, and I can see all the things you did right. All right, let's take a look at a different problem. Again, anytime, ask questions, please. Today's about that. A sample of 26.81 mils of 0.1 molar HCl reacts completely with a rock containing a calcium carbonate. What would be the maximum theoretical volume of CO2 collected at 30 degrees and 1 atm? Other products are salt and a liquid. So what I'd like you to do right now, can you figure out, I'm going to write it up here once, just for me, what is this reaction? So I'm going to pause it if you're at home. So that's what I got from just the actual words. If you have them in the wrong spots, that's what I've picked up so far. It says HCl reacts with calcium carbonate. What would be a maximum volume of CO2 collected? So that would be something that was created. So what else? What did someone else come up with? Salt and a liquid. Give me one of them. Water? Yeah, definitely water. There's H's and O's. Okay, you can write it as HOH if you want, or H2O. That's my liquid. So I still need a salt. So what's left? The salt's usually a metal and a non-metal. And it's just literally what hasn't been used. Next. CaCl. Yeah, and I'm going to write it as CaCl2. So whenever I write a salt, salts are ionic compounds. I have charges. And we haven't really focused a lot on recreating reactions as much as we will as we continue on. What's amazing about this is it's almost balanced. It's very, very close. I think that's it. Correct me if I'm wrong, but I think that's all that's going on. So let's be really clear here. See this, and then I'm going to let you get started here. This, okay, let's talk about what we know. I want this, right? I want volume. So let me even be more clear. I'm going to want liters, right? How do I know liters? Because that's the default that we go to. So I have milliliters and a molarity here of my liquid. Okay. Sorry, I should have underlined all that. And then it says reacts completely with a rock containing this many grams of CaCl3. All right. So you're like, oh, it's a limiting reactant problem. That could be. It definitely could be. But here's the key word, and this is all that I need. And I'm going to make an assumption today. You could definitely find the moles of both. You could. You could do a 3.1. I feel like this problem has tipped its hand to me. Okay, and I want us to just get started because this is actually from last chapter or 2 chapters ago, and I want to focus on the gas part of this, which is the ending here. If I was given the molarity and the volume, can I find moles from this? I hope you feel like you can, because molarity is moles over liters, and if you multiply by liters, you get moles. Can I get moles from grams? Definitely, right? I can do that as well. But the way that it's worded, a sample of this reacts completely with a rock containing that. I feel like it's tipping off, and just due to time tonight, I'm kind of giving you, I'm going to bail us out of a limiting reactant. I could find moles of this, and compare it. Instead, let's just jump and assume that this is the limiting reactant. So what I'm going to do, this is the only part I'm going to start you with. I know you can do this, but I want to make sure that we are just moving forward. So that's of HCl. So once you get that, how do you keep going forward from that? Okay. So I have moles of HCl. I want to have liters of CO2. All right. So think about what you need to do, and then we're going to change gears big time. So let's take a couple minutes and try to figure this one out. If you are getting stuck, I'm still not going to do it all yet, but imagine where you are and where you want to be. So I want to take this path, and oh shoot, I'm not at STP. If I were at STP, I could use 22.4, but I'm not. So I have to take a little bit of a detour. The detours are the ideal gas laws. So this is the opposite of the first one. I'm starting with a T-chart. I'm ending with, and I actually, some of you are a little confused because I didn't quite do this right. I don't have that exactly. That. Because it's a solution, my fault. I'm actually starting right here. So this is even shorter. I kind of got it in the mold already. Right? So, 2 moles of HCl. I have 1 mole of CO2. Okay. That's not difficult enough. And then I need to plug it in. So again, I would love to see this. V equals V of CO2. And then I plug them all in. I put my numbers. I'm trying to tell a story. The better storyteller you are by having some nice descriptions showing my equations, placing my numbers where they should be with units, the better off you're going to be. That's almost scientific notation worthy there. My pressure is in ATM again. And I'd have that for my volume. So it would make 32 milliliters of CO2. Okay? All right. Again, questions if you have them. It's really important. I don't get where you have that number or where this came from or how do you know? Those are the things that tomorrow they're going to get you. You can't have an aha moment after the fact. It needs to be, oh, shoot, wait, I didn't quite understand where that kind of came from in the beginning. Okay, changing gears. An unknown gas has a density of that, 7.06 grams per liter at a pressure, 1.5 atm, and 280 Kelvin. Calculate the molar mass of the gas. I think you should all be able to do this. Shouldn't take all that long. Make sure we have the proper units. Let's give it a shot. Go for it. So there will be problems just like this. They're going to be worth about 3 points, just FYI, or 2 or 3, and gas stoichiometry will be around 4 or 5, or maybe only 4. But I want to give points for things that you're understanding and how to do it. In this case, did you put all the units? Do you have the numbers where they should be? Do I understand what equation you're doing? Do you have the right answer? And do you have the right units for your answer? So I hope that you wrote grams per mole. Molar mass is grams per mole. You just wrote grams, you will get docked. Not a lot, but you will. So please don't make that mistake. That one isn't overly complicated, but it still matters. All right, then we get to something like number 4. This is going to be really short. Won't be a lot. But what I'd like you to do is, all right, let's talk about it first. What happens to the average kinetic energy of a mole of an ideal gas if? 3 things. The volume is doubled, resulting in a decrease in pressure at constant temp. B, the temperature. So these are statements. You're not changing what the statement is. I love it when I give you things like this and students misread it and then they'll like cross it out and be like, no, it'll be halved. Like that's not what the question's asking. It's saying what is happening in kinetic energy if this happens. Letter B, the temperature is increased at a constant pressure, and C, absolute zero is obtained. So what I'd like you to do, either you can do this on your own or you can just consult with someone else, is usually when we ever ask for what happens, you can be very specific or you can just be, usually it's increase, decrease, or remains the same, or you could say unchanged, okay? Those are kind of what, if you want to be more specific, you definitely can, but let's come up with something. I'm going to give you only about a minute. I'm not asking for justifications necessarily. So I just want, where do you think it's going to go? If you have a couple quick words that you want to add to it, that is fine. But let's have a quick explanation or a quick description of what you think is going to happen in kinetic energy. All right, so the volume is doubled, resulting in a decrease in pressure, constant temperature. So the pressure is going down because I doubled the volume. The average kinetic energy will, what did someone write? Luke, what'd you put? So no change, nothing? Good. I will agree. I will just write it kind of under this one. No change. You could have worded it many ways. Not a great question in the fact that it's not guiding you to what answer, but at the same time, it's kind of free to allow you to do whatever. The temperature is increased at a constant pressure. Sammy, what do you think for that one? Yeah, increase. I would definitely agree with that because we know that kinetic energy is dependent on temperature, right? So they put this really long statement on that first one about volume and pressure, and they're trying to confuse you. Last one, absolute zero is obtained. I need a little more than no change or increase or decrease. Sarah, do you have anything for that one? As I then tell you exactly what I'm looking for. Do you have anything for that one? No? Caitlin? It stops. So kinetic energy, let's use it a different way. If it has a value, kinetic energy is now, it's also zero. Why? Because if there's no motion, then there's no kinetic energy. So we could just write it something like this, goes to zero. You could say it decreases, that's definitely true, but the problem is there'd be no kinetic energy because there's no motion. Okay, so kinetic energy based on temp, right? You can just get that down. Everything else they throw at you, they're trying to confuse you. The minute they talk about speed, that is different than kinetic energy. So please be careful on that. Speed is the lightest molecule. Kinetic energy is based on temperatures, how much energy, because it has to deal with velocity and mass, and they're related to each other. All right, let's move on. Another problem. What volume of hydrogen gas at STP will a 0.1 gram sample of magnesium produce when reacting with an excess of HCl? Okay, so the minute I see this, check this out. Hydrogen gas and magnesium. They're talking about two different things. I want to know the volume of hydrogen gas, and I have a sample of magnesium. This, again, is gas stoichiometry. This is stoichiometry because I'm going from one thing to another. So I do need an equation. So please come up with it. Don't look up until you have figured it out. I'm going to do it right now. Read it a couple times if you're not understanding it. There's always a keyword somewhere. In this case, it's reacting. Oh, those are the ones reacting. Okay. Okay, put those as my reactants. Paige, can you shed some light on how this one is different than the other two that we did already today? It's at STP. Right? Now, you could use an ideal gas law. STP means 0 degrees Celsius and 1 atm. And you could plug it all in. But there's a relationship there already. There's a huge relationship. So I'm hoping that you can execute this. Please go for it. This one's a lot shorter than the first two that we did. Done, you can look up, see if you get it right, and that would be the volume of my hydrogen. So that's nice and clean. STP gets me my 22.4, right? So that is my STP relationship. And if you're ever not sure where that all comes from, if you did volume equals nRT over P, and you made this 1, you made this 273 Kelvin, and you made this 1 ATM, it automatically becomes 22.4 liters. That's where it results from. So 1 mole equals 22.4 liters. That's my wish. Good. Okay, we're cruising. Okay, here we go. Calculate the rate of effusion of pH3 molecules through a small opening if NH3 molecules pass through the same opening at a rate of 8.02 centimeters cubed per second. Woo! Assume that the same temperature and equal partial pressures of the two gases. All right. Wow, there's a lot going on there. So, let me try to, if you had to run into something that was a little different, what am I saying? Well, first off, we're using this equation. Now, normally, we write this. And then that can give me a rate. So, what I'd like you to try to do, this is one of those, can you go a little, it's a half a step. This equals, when I get an answer, this says how much faster the rate of one is versus another. Okay? Well, if I know the rate of one of them, could I figure out the rate of another? Okay, so basically, let's just say, now maybe I don't need to get this away. Do I want to get this away? If I figure this out, let's just say that the lighter one versus the heavier one is 10 times faster. If I knew the rate of one of them, then can I use that rate, the magnitude of the rate to figure out the actual speed of another one? Because it was either 10 times faster or 10 times slower. I guess is what I'm trying to tell you. Solve for, I said more than I wanted. Solve for how much faster or slower they are to each other and see if you can apply it to the rate that it gave you. Maybe that'll help. Okay? So, you always use this equation first and use the molar masses. Which one is going to be faster without even doing a calculation? Which one's faster? pH3 or NH3? NH3 is the lighter one. So that means that NH3 has got to go here. And that means it's got to go here, right? You always want to put the fastest one on top. Unless if you're actually talking about how much slower the other one is. Right? Give it a shot. See what you come up with. Okay. There's two different ways you could have done this. If you're finishing it up, still keep going through it. But first, you could have actually figured out how much slower than the other one is. So you could have actually flipped this. But I'm going to keep it the way that we have this right now. So if I have rate of NH3 over the rate of pH3, so I have 33.97, I think. I got roughly 1.41. Okay. That's saying that ammonia effuses 1.41 times faster than pH3. So you could have done it some ways. Now, this is one way you could have done it. Said, okay, if that one's faster, if I take, this is not the way that I guided you there. If I take the reciprocal of it, then that's 0.709. What am I doing by that? What I'm saying is that the pH3 is about 71% as fast as the NH3. So you could have taken 0.02, 8.02. You could have multiplied it by how much slower the other one is, or it's in the equation itself. You did rate over the other rate. So if I have one rate over the other, check this out. The rate of this is 8.02. I'm hoping that some of you saw it, how this worked. And the other rate is unknown yet. And what I know is that the comparison between them is that it is 1.41 times faster. So that math right there, either one gets you to 5.69 centimeters cubed per second. It has to effuse at a slower speed. And I know that seems weird, the centimeters cubed per second, but don't worry about that part. Now you're like, whoa, whoa, you never taught this. You got to kind of recognize, well, what does this mean? That final answer, whenever you do an effusion problem, that final answer is the comparison of one rate to the other. And if you know a rate or you know something else about it, you can apply that in many different ways. So this was two separate ways that you could have done the ending of that problem. Okay, the first one again, well, that's that much slower because I'm going to take the reciprocal. I'm taking the reciprocal of all of this. It's 70.9% slower than that rate. Or you could have put it back in the actual words of rate and said, well, that's the overall. So hopefully that's not too mind-blowing. All right, moving through. Only a couple left. All right, this one's short. I'm not looking for a long answer, but I want something. So again, I like you to work with someone else. A man in Alaska claimed that he was cheated when he bought a 40 liters of hydrogen gas from a warehouse in Florida and only received 39.67 liters. As the lawyer for the chemical warehouse, what is your defense? Be specific. So you should cite something, I hope. Maybe it's a sentence. Maybe you're using equations. Maybe you don't really have a lot of math you can do, but you could create something if you'd like. What's your defense? Please, no more than probably 2 sentences or a very small amount of work. But what are you going to come up with? You can talk to someone else or compare when you are done. Okay. What's your defense? Let's go for it. Yeah.
Would the volume go down because you're going from a higher temperature to a lower temperature?
Sure. What could I write down? That's right. What could I write down as a chemist? What could I show? What law can I write? Yeah, I could discuss this a little bit. You could have. I don't know if you chose to do this. Sometimes, I know many of you, if you don't know how to start something, start making up things like values within an equation. I'm not. Whoops, I said the wrong one, didn't I? Why did I say pressure? I was all excited. We're talking about volume. It would deal with pressure, but we don't know the pressure. There we go, Charles' law. But I could make up something like the temperature, or I could actually, if I was the lawyer, I could actually say what the pressure or the temperature was in Florida, but maybe it was, like 25 degrees, and in Alaska now it's 5 degrees. I'm talking in Celsius, not in Fahrenheit. And then that can prove the differences in that volume right there. So I could use Charles' law. So your defense, regardless, is Charles' law. That would be kind of where you're going, if you wrote it down or not. But I guess why I bring this up is if you're ever trying to explain something and you're just stuck, or you feel like, I just don't have enough, why not use an equation, and then you can say, according to the following equation, it would cause this value to increase or decrease, or the relationship is a direct or indirect relationship. You could talk about it by using a law that's been proven, and that works. Okay, so don't let that. Now, you can't just write that down and drop your pencil and be done. You cannot do that. You can't just go Charles' law. I said it. I said Charles' law. You need to explain more. So as the temperature goes down, the volume goes down. You'd have to say something according to Charles' law, and you'd be good. You'd make it. Okay, so it's a good tool to have, and I don't think people use it enough. And just don't use that's the only thing. You need a little something in there. But that's kind of like a picture says 1,000 words kind of deal. This really helps explain it, and you don't need to explain every single thing. You do not need to say, well, what you do is then you cross multiply and then you divide it, and that would solve for the other v. None of that that's way overboard. 2 left. What pressure will 30 grams of NO, 36 grams of H2O, and 46 grams of NO2 gas exert in a 3-liter container at 79 degrees Celsius? Before we start, I want you to help me start this. We did one earlier today. I want the shortest route possible. So what's a goal? What could I do? How do I approach this? I want pressure. Okay. I have grams of all these gases. I have a volume, and I have a temperature. Here's. Okay. Okay, so I'm going to find, basically what you're saying is I'm going to get moles of each of these. So do 1. So what I want is this. You were correct. Right? That's what I want. Now, you could go about this in other ways. You could do P P sub NO, pressure of NO nRT over V, the pressure of H2O nRT over V, and the pressure of NO2 equals nRT over V, and then you add each of those pressures up. That's a lot of work. So this, I believe, is the shorter way. So again, we want to make sure that we understand this. Let's take a little time to finish this one up, and then we'll end on a much shorter question. So you get your 1 mole, your 2 moles, your 1 mole. I don't know pressure, so I'm going to use this one. I need to get that one wrong off the top of my head. If you chose a different R value, believe me, I will calculate it. It's not like, shoot, I guess Tor and he picked KPA. I'm going to do it. As long as you use the proper R value, I will convert it. I will take your answer and I will probably divide it by whatever I have it in. Divide it in ATM and you do KPA, I'll probably take your answer and divide it by 101.3 to see if it's the same ATM. You're not going to get away with it like, ha ha ha, he won't calculate it. But, you know, as long as you notice what you're doing. So this would be this is the shortest way. But whatever works in your brain, in your approach, and sometimes you go down the wrong path and then all of a sudden you find yourself, it's fine. That's why it's really smart. Start as far left as you can. Those of you that start in the middle and think you only have a little work and they're like, oh my gosh, wait, I gotta still do this. Next thing you know, you're all the way back in a circle, and that gets really confusing. So try to keep it from left to right. Final one today. This is actually from an old AP exam, not like my exam, like the actual AP exam. And I just wanted to talk about 2 free response answers. So it says an experiment, and I know there's a lot written here. The reason why there's so much here is that there's actually, there was a lot more to this question, but we aren't quite there yet, and I didn't want to spend that much time on it anyway. In experiment, all the air in a rigid 2-liter container flask is pumped out. Then some liquid ethanol is injected into the sealed flask, which is held at 35 degrees. The amount of liquid ethanol initially decreases, but after 5 minutes, the amount of liquid ethanol in the flask remains constant. Ethanol has a boiling point of 78.5 degrees Celsius and an equilibrium vapor pressure of 100 torr. Don't freak out about that. Basically, that's the pressure that's coming, like that's present in that container. It's how much pressure is coming off of that, that liquid at that same temp, or at 35 degrees. Sorry, which that's what they're at. They're at 35 degrees. Okay. So that means it's not boiling right now. It just naturally, some of it evaporated. We all know you put water on the table, it's not like it stays here because it's not at 100 degrees Celsius, so it's never going to leave. It slowly evaporates. Molecules still evaporate on the surface. So A and B. When the amount of liquid ethanol in the flask is constant, so you can come back up here and see when it's talking about being constant, is the pressure in the flask, here I go. If they give you options, you need to use these exact phrases. Drives me nuts when it says greater than, less than, or equal to, and someone will use something like it'll be much bigger, or it'll be lower. I can't remember some of the examples. I mean, they're hilarious. Or you'll flip it and you'll actually talk about the other direction. So you're trying to say, like, is this thing lower than this one? And you'll go, no, this one is higher than that one. Like, what did you just do? And, like, you did. Well, I said it. I'm like, no, but you didn't. Like, you can get that wrong. Like, you got to be really careful. So, let me go back to it. When the amount of the liquid ethanol in the flask is constant, is the pressure in the flask greater than, less than, or equal to 100 torr? Justify your answer. I'm just getting us to think about how, with pressures and volumes and everything else, we're going to kind of answer this together. These are really short answers, actually. This is the beginning of a big problem. But what do you think? Is the liquid ethanol in the flask, when it's constant, so at some point it stopped evaporating, I have gas and I have liquid, is the pressure in the flask greater than, less than, or equal to 100 torr? Justify your answer. So, let's go back. It says that the amount of liquid in ethanol initially decreases. Why does it decrease? Because some of it becomes gas. So I have liquid, and then I get a little bit of gas. After 5 minutes, the amount of liquid stays the same. So that means I have the same amount of liquid and the same amount of gas after 5 minutes. Okay? So blah. At equilibrium, which this is why it's a little hard to talk about, but that means that nothing's changing. So I have the same amount of liquid and gas. At equilibrium, I have 100 torr for my pressure. So when the amount of liquid ethanol in the flask is constant, is the pressure in the flask greater than, less than, or equal to 100 torr? What do you think? Just based on what I just told you. It is equal to. And here's the answer. Equal to 100 torr. And I'll change the word, the answers a little bit, but because the gas and the liquid remains constant. Like nothing's changing anymore. Right? If you add more gas, don't you gain more pressure? Right? The more gas you get, if it keeps evaporating, guys, you're going to gain more and more and more pressure. If it keeps evaporating, more and more pressure. It's saying after 5 minutes, nothing changed at all. So that means that that is the pressure. Nothing's changing. So that would be equal. That'd be a point. If you got it, great. If you just understood what it was saying or not. Letter B, finish it up. The flask is then heated to 45 degrees, and the pressure in the flask increases. In terms of kinetic molecular theory, provide 2 reasons that the pressure in the flask is greater at 45 degrees than at 35 degrees. And you're going to laugh when you see all 3. There's 3 options that they gave. This is why I was looking for my print off. They almost all seem exactly the same, but they're not. So what it's basically asking is why do you, after you increase the temperature, why is the pressure increasing? So I have these molecules in here, right? And now I'm heating it up. Here's my flame. Wow, that's awesome. Assuming it's on a Bunsen burner, I don't know. And I'm giving things away already. I'm moving around. So what's something that would increase pressure? True, but we got to say something a little more specific than that. You're right. Yes. Both are true. We still have to connect it to pressure, is what I'm saying. Oh, is that a hand? Trevor, you're giving me a hand. Go. What do we link with pressure?
No idea.
Pressure. Luke, more collisions where? This is why you're going to start laughing. What? Against the molecules? So, greater pressure, more collisions with other molecules. Let's call them particles because I can spell it faster. With other particles. Which technically, I'm still. This is okay. This is anything else about collisions. I'm actually I shortened this up. I should have said it that way. More collisions with the other particles, but actually more specifically, where else are the collisions going to happen? On the wall. Let's say a flask wall. This is going to be ridiculous when we break this down. What else happens on the flask wall? If you have, if you speed them up, what about the collisions? They're going to be maybe more forceful. So greater collision force on the wall. So those would be your 2 answers already. And then the last one, if you are speeding them up, then the wording is so funny. Hold on. We'll just leave it at that. I feel like there's 2 of them. Literally, it says there's more collisions on the wall, and then because of the speed, there'll be more frequently. The collisions will happen more frequently. I'm like, well, what's the difference with that saying more collisions? So, whenever you're talking about pressure, I guess what I want to get across, and I'm glad you guys said to what you said, when you're talking about pressure, it's always about collisions. Do you have more collisions? Do you have less? You add more particles in there, you get more collisions because you just have more things running into the wall. Okay? Bookwork tomorrow. Gases 4 and the volatile liquid lab. A lot of you have been handing some of that in already.
Yeah.